Hi, myself Syed Mohammed Basha. Today, let's see a second year chapter, as you know, that is solutions. Okay, so according to a NEET syllabus, we may expect 2 or 3 questions from this chapter. So that's why we have a percentage of asking questions here somewhat more. That's why we should give importance to this chapter. Okay, so now let's start with the synopsis. Afterwards, we will see some MCQs. Okay. Now let's see solutions. As you know, solutions is a homogeneous mixture of 2 or more components. Okay, but here in this chapter we are restricted for only 2 components. Okay, so that's why here we have only 2 components. One is solute and one more is solvent. Okay, so you know this is a solution in which we have solute and one more is solvent. According to definition, we can say it as solute is in a lesser quantity and solvent it will be in a higher quantity. So if you come to the classification, let's see the solutions. We are going to classify solutions based on different things. That is first one, types of solutions, and second one, measuring concentration of solutions, and third one depends upon solubility of substances. Okay, first one, let's see. As I already told you that it is a binary solution. So that's why here we have only 2 components. Based on that, we are going to get 3 types of solutions. First one is gaseous solution. Here the solvent is gas and the solutes are solid, liquid or gas. Okay. So next that is liquid solution, and third one it is a solid solution. As you know, in liquid solution we have solvent that is liquid, and in case of solid solutions we have solvent that is solid. Okay. So next one, let's see the examples. That is in gaseous solution, as I already told you, here the solvent is gas and the solutes are maybe gas or liquids or solids. Okay. So in case of liquids, here the solvent is liquid and the solutes are gas or liquid or solid, and solid solutions. So we have that is solvent that is solid, and solutes are gas, liquids and solids. Example for gas in gas, that is mixture of H2 and Cl2. Example of liquid in gas, that is water vapor in air. Example of solid in gas, that is copper in gas, and gas in liquid, that is chlorine in water. So next liquid in liquid, that is acetic acid in water, that you call it as vinegar. So next liquid in liquid, that is acetic acid in water, and solid in liquid, that is NaCl salt in H2O. And if you come to a solid solution, here gas in solid means that is H2 gas in palladium, and liquid in solid, that is gelatin, and solid in solid, that is, you can give any example of alloys. Okay. So if you come to next classification, that is measuring concentration of solutions. You know, amount of substance in particular solution gives a concentration of the solution. So based on that, we are going to have a different terminologies, that is concentration terms. Very first one, that is mass percentage, and next is volume percentage, and next is mass by volume percentage, and next is parts per million, molarity, molality, normality, formality, and mole fraction. In first year we have seen some of this like molarity, molality and mole fraction. Remaining we will see in this section. So all these I have briefed here. So first one, that is mass percentage. We have a formula, that is W1 divided by W1 plus W2 into 100, because here we are going to calculate the percentage, that's why. Okay. So next volume by volume percentage, here we have V1 by V1 plus V2 into 100. So in case of mass by volume, we have W by volume into 100. So in case of first 2, we don't have any units because they will get cancelled by each other. In case of mass by volume percentage, we have gram per liter as a unit. So next parts per million. You know, million is 10 to the power of 6. If you want to calculate any minute quantity concentrations, we are going to use this concentration term, that is parts per million. Okay. So next here the formula is W1 by W1 plus W2 into 10 to the power of 6. So in case of molarity, you know, in first year also we have a definition, that is number of moles of solute dissolves in 1 liter of solution, that is called as molarity. It is denoted by capital M, and it's having a unit, that is moles per liter. In case of molarity, we have a quite little bit difference from molarity, that is number of moles of solute dissolves in 1 kg of solvent. It's having a unit, that is moles per kg. Next, in case of normality, it is similar to molarity only, but here we have a difference. Here it is number of moles of solute, but here it is gram equivalent weight of solute dissolves in 1 liter of solution. That's why its unit is equivalent mass divided by liter. So next formality, here gram formula mass divided by 1 liter of solution. Next mole fraction. You know, mole fraction is not going to explain the concentration of total solution. It's going to explain or give information regarding the component of only one, either it may be solute or solvent. For that, so n divided by n plus capital N. Here small n represents solute or capital N represents solvent. Next, as I told you, measuring concentration gives the strength, so that is strength of solution. We may dilute it, the solutions. Okay, so for that we have a small formula, that is dilution law. M1V1 is equal to M2V2. In case of normality, it is N1V1 is equal to N2V2. So next, we have seen solid in liquid. So before that, so again, next solubility of substances. Okay, based on this type of solute, dissolved in type of solvent, we are going to classify these three. That is solid in liquid, liquid in liquid, and gas in liquid. Let's see the first one, that is solid in liquid. So in case of solid in liquid, here we may get three types of solutions. One is unsaturated solution, one more is saturated solution, and one more is supersaturated solution. It depends upon the types of solute and solvent what you have taken, because we have a relation, that is like dissolves in like. That means organic dissolves in organic solvents, inorganic component dissolves in inorganic solvents. It won't be crash. Okay, that's why polar solute dissolves in polar solvents and non-polar solutes dissolves in non-polar solvents. So now, solubility of solid in liquid is affected by first factor, you know, that is nature of solute and nature of solvent, and second factor would be temperature. Okay, so how it affects, let's see. So in case of temperature, we have two types. One is endothermic reaction and one more is exothermic reaction. If the solubility of solid in liquid leads to an endothermic reaction, then solubility increases with increase in temperature. If the solubility of solid in liquid is an exothermic reaction, then the solubility decreases with increase in temperature. It is quite important, so remember it. Okay, so after that, let's see the next classification, that is liquid in liquid. Here we have three types. One is miscible, that means dissolves completely in each other. So next, immiscible, do not mix with one another. Okay, and in case of partially miscible, here dissolves up to a certain extent, not completely. Okay. So next, liquids in liquids. So in case of liquids in liquids, we have seen this one. So in case of immiscible and miscible and partially miscible liquids, we are going to get a azeotropic mixtures. So azeotropic mixtures means they will having a boiling point same at solution phase as well as in vapor phase. So here we are going to get two types of azeotropic mixtures. One is minimum boiling azeotropic mixture and one more is maximum boiling azeotropic mixture. In case of minimum boiling azeotropic mixture, solutions having boiling point less than either of its pure component. In case of maximum boiling azeotropes, solutions has boiling point more than either of its pure components. So next we have, that is gas in liquid. Here also we have a gas that acts as a solute, and here liquid acts as a solvent. In case of this, we have factors which affect the gas and liquid dissolution. That is first one, nature of gas, and next one is nature of solvent. As we already know, like dissolves in like. Okay, so that's the factor which comes under these two. And next one, temperature. As you know, as the temperature increases, solubility of gas and liquid decreases. That means decrease with increase in temperature. And here we have a effect of pressure also. That is increase with increase in pressure. If you increase pressure, the solubility of gas in liquids increases. So based on that, we are going to have an important law, that is called as Henry's law. It gives a quantitative relation between solubility of gas in liquids. Okay, so it gives a formula, that is solubility of gas is equal to K into Pg. Okay, where K, it also called as KH, it stands for Henry's constant. So next, here we are going to have a vapor pressure. Vapor pressure exists when a solution having equilibrium with its vapors. Okay, so that time we are going to get a vapor pressure. So vapor pressure of the solution depends upon these factors. The first factor, that is factors affecting vapor pressure of solution. Next one is, as you seen, that is gas dissolved in liquids, that gives Henry's law. Here liquids dissolves in liquids, that gives Raoult's law. So next Raoult's law, volatile, that will comes and we can classify twos, that is Raoult's law of volatile solids and Raoult's law of non-volatile solids. So in case of factors affecting vapor pressure of solution, first purity of liquid is very important, because here we are going to see the solutions. So for the solutions, vapor pressure is always less compared to its pure components. That's why always has a higher vapor pressure than its solution. Okay. So next one, nature of liquid decreases with increase in intermolecular forces. Nature of liquid, that means if interaction is more, then the vapor pressure is less. If the interaction between the molecules is less, then the vapor pressures are more. So next, temperature. As you know, in the solubility of liquids in liquids, it increases with increase in temperature. Next, effect of adding a solute. As you know, in solutes we have two types. One is volatile and one more is non-volatile. So if you add a non-volatile solute, then it is decreases. When you add a volatile solute, then the vapor pressure is increases. If you want a relation between solubility and temperature, we have an equation. This equation is ln P2 by P1 is equal to delta H divided by R 1 by T1 minus 1 by T2. It is called as Clausius-Clapeyron equation. Next, if you come to Raoult's law, you know this Raoult's law is for solutions which is having liquids in liquids. Okay. In case of liquids in liquids, it comes under Raoult's law. It says that if you want a component in a mixture of solutions, okay, the vapor pressure, I mean the partial vapor pressure of the component in vapor phase is directly proportional to mole fraction of that component in the solution phase. Okay. So based on that Raoult's law, we are going to classify solutions into two types. One is ideal solution, one more is a non-ideal solution. Here ideal solution means it obeys Raoult's law. Non-ideal solution means it does not obey Raoult's law over a range of temperature and pressure. Okay. In case of ideal form, that is P total is equal to PA plus PB. As from Raoult's law, we know PA is equal to PA naught XA for component A, and PB is equal to PB naught XB for component B, so that we can write it as PA naught XA plus PB naught XB. Totally, here we are going to take a common, that is we can write XA as 1 minus XB. So at last we will get P naught A plus P naught B minus P naught A XB. Sorry. So this is the final equation we are going to get for ideal solutions. In case of non-ideal, as you know, it is not equal to PA is not equal to PA naught XA and PB is not equal to PB naught XB. Okay, so this is ideal solution and non-ideal solution. We have plenty of example for this one. Okay, so now let's see the next one, that is Raoult's law for volatile solutes. So for that, you know, that is P is equal to P naught X. If you take it for A, then PA is equal to P naught XA. For PB, it is PB is equal to PB naught XB. So in case of Henry's law and Raoult's law, we have only these differences. That means constant differences. Here we have P naught, that is partial pressure of pure component. Here we have a KH, that is Henry's constant. That's why these two laws, I mean Raoult's law as a special case of Henry's law. Okay. So for case of non-volatile solutes, okay, here we have a solution, total solution, that is P naught solvent and X solvent. It indicates that so relative lowering of vapor pressure is directly proportional to mole fraction of solute dissolved in that. Okay, so that's why. So these are the vapor pressures of solutions which affects and the factors, all those things. Okay, so next we have colligative properties. As you know, colligative property is a property. It depends only on number of solute particles dissolved in the solution, not on the nature of solute particles. Okay, based on that, we have seen mainly 4 colligative properties. First one, that is relative lowering of vapor pressure, and next one is freezing point of depression, and boiling point of elevation, and osmotic pressure. And to correct these things, we are going to study one more factor, that is called as Van 't Hoff factor. In case of relative lowering of vapor pressure, we are going to calculate the molar mass by using the formula, that is P naught minus Ps divided by P naught is equal to W by M into M divided by W. Okay. So in case of freezing point depression, delta Tf is directly proportional to molarity. So here we are going to get a a constant that is called as Kf, it is considered to be called as molar depression constant. If you introduce n factor, that gives delta Tf is equal to I Kf into m. If you want to calculate molar mass, we have a formula that is delta Tf is equal to Kf into W2 into 1000 divided by M2 into W1. Same in case of boiling point also, delta Tb is directly proportional to molarity. So here we are going to introduce a constant that is called as ebuloscopic constant, that is denoted by Kb. Okay, if you want to calculate the molar mass, delta Tb is equal to Kb into W2 into 1000 divided by M2 into W1. In case of osmotic pressure, you know osmosis, that is movement of a solvent particle from lower concentration to higher concentration is called as osmosis through semi-permeable membrane. Okay, so if you want a osmotic pressure, that means an excess pressure applied on a higher concentration side just to stop the osmosis process. For that, we are going to represent osmotic pressure. It is by the equation that is pi here directly proportional to concentration. Okay, so if you remove that, if you equate that, then pi is equal to MRT, where M is molarity. Okay, if you want to calculate molar mass, then you have a formula that is M is equal to pi is equal to MRT. And next we have Van 't Hoff factor. Van 't Hoff factor is a term used to solve the abnormal molar masses. Okay, so abnormal molar masses comes because of these things. Okay, so if you want to clear that, we need to introduce a Van 't Hoff factor that is denoted by I. Here we have two types. One is degree of association and degree of dissociation. For degree of association, alpha is equal to n into 1 minus I minus 1 divided by n minus 1. In case of degree of dissociation, alpha is equal to I minus 1 divided by n minus 1. Okay, it is all a brief synopsis regarding a solution. We have not gone in detail regarding this thing. Just we have seen the flow charts. Okay, now let's solve some questions about this. That is MCQs. So let's see. All these questions have been asked previously. So one or the other form. Okay, so I have put such type of questions only. So let's see the first question, that is, if molarity of the dilute solutions is doubled, the value of molar depression constant Kf will be. As we know, here it is a depression constant, that means molar depression constant. You know that is delta Tf is directly proportional to molarity, and we have a constant that is Kf. That means it doesn't have any relation with the change in concentrations or temperatures. Okay, so that's why. So it's having a it doesn't having any difference. That's why it is a constant. So we can have options that is doubled, half, tripled, or unchanged. It is a constant. That's why the answer is unchanged. So let's see the second question. That is, which of the following is dependent on temperature? As we see already, that is the concentration terms, molarity, mole fraction, and all. So there, if we have any volume term in any of these, I mean in either in upper side or lower side, so that affects the concentration. So if we don't have volume term, it is independent of temperature, because temperature is directly proportional to 1. If you see that one, that is molarity, mole fraction, and weight percentage. In these four, we have a molarity, that is a volume term. That means it is dependent on temperature. That's why option B is the answer. Next, of the following 0.10 molar aqueous solutions, which one will exhibit the largest freezing point depression? Okay, so freezing point depression, you know that is delta Tf is equal to I into Kf into M. Okay, so that means here I factor includes, I mean Van 't Hoff factor is includes. Van 't Hoff factor for KCl, that is 2. So here it is glucose, it doesn't dissociate or associate, that means I is equal to 1 it is. And here Al2SO4 thrice. If it dissociate, it gives 2Al3 plus and 3SO4 2 minus. Totally it will become 5. And here also we have 2K plus and 1 SO4. That means this is 2, this is 1, this is 5, and this is 3 I factors. So which one is having highest I factor means that is option C. So that's why option C will exhibit the largest freezing point depression. Next, here PA and PB are the vapor pressures of pure liquid components A and B respectively of an ideal binary solution. If X represents the mole fraction of component A, the total pressure of this solution will be, they have given. Okay, so while studying ideal gas equation, we have got one equation, okay, that is P total solution, okay. So based on that, if you see that options PA plus XA, PB minus PA, so here it quite looks not good, okay. So in case of second one also PA plus XA, PA minus PB, this is also having a reverse order. So next in case of C, PB plus XA bracket PB minus PA, this is also somewhat here we should have a PB term. So here we have PB plus XA, PA minus PB. If you write the equation for that, you will get option D as an option. Next, the Van Gogh factor I for a compound which undergoes dissociation in one solid. It is undergoing dissociation in one solid and association in other solid is respectively. They have asked a question. So that means we know I is greater than 1 means that is dissociation. If I is less than 1 means that is association. So here it is undergoing dissociation means this is greater than 1. If it undergoes association means that is less than 1. For that, option A, less than 1 and less than 1, both not same. Greater than 1 and less than 1. Greater than 1 and greater than 1. Less than 1 and greater than 1. In case of dissociation, it is greater than 1. That means first one greater than 1. And next one association, that means less than 1. That means option B is the answer. So next, an increase in equivalent conductance of a strong electrolyte with the dilution is mainly due to, okay. So increase in equivalent conductance, that means conductance is increasing. If you want to increase the conductance in solutions means you need ions, okay, that too a fast moving ions. That means let's see the answers. Here we have answer A, that is increase in ionic mobility of ions. 100% ionization of electrolyte at normal dilution. Anyhow, if it is strong electrolyte means 100% dissolution only. So increase in both the number of ions and ionic mobility of ions. If it is a strong electrolyte means obviously it undergoes dissociation. That doesn't matter here. So next D, increase in number of ions. Okay. So option here is option A, that is increase in ionic mobility of ions. That what gives the increase in equivalent conductance of strong electrolyte. So that is increase in ionic mobility of ions. So next question number 7, a solution of acetone in ethanol. So as we see, two types of solution, that is ideal solution and non-ideal solution. So this acetone in ethanol is comes under non-ideal solution. That too we have two types, that is positive deviation and negative deviation. So acetone and ethanol combination or alcohol or water combination comes under positive deviation, and water and acids combinations comes regularly comes under negative deviation, non-ideal solution. That means it's an example of positive deviation. That means option B shows a positive deviation from Raoult's law. Option B is the answer. Question number 8. During osmosis, flow of water through a semi-permeable membrane is, as I already told you, that is osmosis is a process in which movement of solvent particles, that is pure solvent particles from higher concentration, lower concentration to higher concentration, they will move through a semi-permeable membrane. That means here the option is from a solution having higher concentration only, no. From both sides of the semi-permeable membrane with equal flow rates, no. From both sides of semi-permeable membrane with unequal flow rates. Next, from solution having lower concentration only. So according to definition, option D is the exact answer. That is from solution having a lower concentration only. So next, question number 9. Which of the following statements about the composition of the vapor over an ideal 1:1 molar mixture of benzene and toluene? So this will come under ideal solution. As an example of ideal solution is correct. Assume that the temperature is constant at 25 degrees Celsius. They have considered at 25 degrees Celsius. So they have given some data. That is vapor pressure of benzene, that is 12.8 kilopascal, and that of toluene, that is 3.85 kilopascal. As you know, as the temperature increases, vapor pressure is also increases. That means it's having a direct relation. That means which one is having a higher pKa values, that will have a more vapors. That means option here is the vapor pressure will contain a higher percentage of toluene. No, because the toluene is having a less value. The vapor pressure, the vapor will contain equal amounts of benzene and toluene. No, we have two different values here. So not enough information is given to make a prediction. We have sufficient information to predict that. Let's see the last one. The vapor pressure will contain a higher percentage of benzene. So your option D is correct answer because benzene vapor pressure has a 12.8 kilopascal. Compared to toluene, it is more. So that's why option D is the answer. Next, in case of 10th question, which one of the following aqueous solutions will exhibit the highest boiling point? So again, we are going to calculate these questions based on Gogh factor only, because here we have solutions having same concentration, these two and these two. If you see the solutions, that is Na2SO4, and this is KNO3, and this is urea, and this is glucose. You know glucose, it is Gogh factor is 1, and here also this is also having 1. But in case of these two, Na2SO4, that is 2 Na plus and 1 SO4, that's I value is 3. Here KNO3, K plus NO3 minus, that is I value is 2. Out of these two, this one having I value more, that's why option A is the answer. So these are the some important questions we have discussed. So remaining a lot of questions are there. Let's detail in the next class. Thank you.